All right, so let's recall when we were proving Theorem 1 in particular, we introduced this curious notation, which was taking a lowercase letter, putting an arrow over it, and we said that when we had a lowercase letter with an arrow over it, that refers to an n by 1 matrix. Remember, n is number of rows, and 1 is number of columns. So if you have a matrix with only one column, that is essentially like a vertical column as such. So you've got n entries in there, you could call them B1, B2, down to Bn. So what we're going to do today is sort of give this object a slightly different name. So we're going to define, call any n by 1 matrix a vector. So the word vector is just going to be something that describes a single column matrix. Vector, single column matrix, vector. So one way to denote vectors is a lowercase letter with an arrow over it. Another way to denote vectors is to just call them what they are, vectors. Another way to denote vectors in matrix form as a column. So the notion of a column, a single column matrix, a lowercase letter with a line over it, and vector, these things coincide. They're just three different ways to represent these objects, and they all are referring to the same thing in essence. Okay, and what we're going to do today is, well, in this series of videos, I suppose, is address the geometry of vectors. And now, when I say geometry, there's going to be a certain point where geometry becomes geometry in quotes, because at some point you can't visualize beyond a certain number of dimensions. So in particular, when we're going to be talking about the geometry of vectors, we're going to use what happens in the 2-dimensional and 3-dimensional cases to describe the n-dimensional case. So ultimately, we're going to take the circumstances that we can see and build up from that to the circumstances that we can't. And that's why I sort of put geometry in quotes here. So we're going to use the geometry quote free in 2 and 3 dimensions to geometry in quotes deal with the n-dimensional case. And here's how we're sort of going to do this, because if we're going to take vectors and we're going to describe them geometrically, then we need a way to visualize them in terms of some shape, in terms of some geometric interpretation. So here's how we're going to do it. So say you've got a 2-dimensional vector like 2, 5. Here is a 2-dimensional vector. I could call this A, I could call this B, I could call this whatever I want, put an arrow over it. This is a vector. Why? It's a single column matrix. Well, to interpret this geometrically, I'm going to interpret this in the xy plane as an arrow that goes 2 units to the right and 5 units up. So when we look at 2, 5 as a vector, we're going to look at this as a vector which goes 2 units to the right and 5 units up. Why 2 units to the right? Well, the first number here we're going to interpret as the x-axis position. You know the right is the positive x-axis. Here, 5, the y-axis position. Again, 5 positive. So the long story short is when we think about this vector, 2, 5, the vector A corresponds to a movement of 2 units to the right and 5 units up. And you could view that as a single arrow to represent the vector. So now you can see how when we talked about the vector as a letter with an arrow over it, how that actually relates to its geometric interpretation. So now I'm circling the arrow as yet another way to interpret a vector. You can interpret a vector as a single column matrix. You can interpret a vector by just the word vector. You can interpret a vector as a letter with an arrow over it. You also could geometrically interpret a vector as an arrow which goes in the direction and the length of 2 units to the right and 5 units up. Now, correspondingly, if you had a vector, let's call it b, and this vector was associated with like 1, 4, 7, well, we could look at this in three-dimensional space, where the 1 is corresponding to the x-axis position, the 4 is corresponding to the y-axis, and the 7 in the z-axis. So here is an arrow, which is signifying a movement of 1 unit to the right in the x position, 4 units up in the y position, and 7 units in the z position. So if we're looking at sort of our standard XYZ picture here, where we've got our x-axis in the positive direction, and our y-axis in the positive direction, and our z-axis in the positive direction, this vector b is going to be 1 unit in the x direction, 4 units in the y direction, and 7 units in the z direction. And there will also be a vector associated with that, a single arrow to describe that movement. And there it is, we call that vector b because that's what it was defined to be. And here is the vector in three-dimensional space corresponding to 1 position of x movement, 4 positions of y movement, and 7 positions of z movement, in particular in the positive direction in each case, since this was a positive 1 and a positive 4 and a positive 7. If you wanted to move left instead of right along the x-axis, you could put a -1 there, and that would correspond to the vector that instead of going right 1, you went left 1, and then the subsequent position movements. But the long story short is, when we talk about vectors, when we talk about single column matrices, when you talk about these objects that we've concisely described algebraically as a letter with an arrow over it, you could also think of these things geometrically as, well, an arrow in 2 or 3-dimensional space.